So I thought I'd start out just sort of giving you a little bit of my background, partly so you know who's talking to you, and partly because I actually think it's kind of relevant in the context of some of the discussions I'm hearing you guys have. Like I basically set out to be an airplane mechanic. Like I went to school, and after 2 years, which I realized, you're talking about 2 years. After 2 years, I was, a licensed airplane mechanic. I actually still have it on my wall. A little card says I'm a licensed airplane mechanic. And I started working on planes. It was before I was an engineer. I was in an aircraft maintenance engineering program. And so I think one of the things that gave me was a different perspective on engineering. Like I backed into engineering from working on machines versus getting all the theory and then saying, maybe I should go try this on an actual machine. So that's what I set out to do. What actually happened is reality intervened. Like my little dream was, okay, so I'm going to go get my aircraft maintenance and engineering degree, and I want to live in Oregon, so I'll get a job working with Boeing, and life will be wonderful. And I got out of school, and Boeing had just laid off 40,000 people, and the last person leaving Seattle signs were up and stuff like that. And basically, I had a mentor from Parks, Al Black, who had left Parks and went to work for this consulting firm named McClure Engineering. And they were really, really good they had realized that the design day is all interesting and everything, but what really matters is the load profile, like the seasonal load profile and the daily load profile. And they had developed a reputation for going into what we would call cogen plants. Back then they called them total energy plants, and making them work. Like these plants would be perfect on the design day, but they'd be a disaster every other day of the year. And so they had gotten really good at that. And actually Al had gone there to write modeling programs. Before the energy crisis, Al had actually written energy modeling programs that they were using to fine-tune the systems and understand the designs. And the other thing they had learned, that in addition to the load profile mattering, was that you couldn't do breakdown maintenance on a total energy plant. Like if the lights got in the hospital or the shopping mall, that's a big problem. And so they were trying to understand how to develop preventive maintenance for buildings. And it occurred to Al, like, wow, David's got an engineering background. He's been working as a mechanic. He's looking for a job because he can't get steady work because of the economy. Maybe it'd be a good fit. And so I went and interviewed, and in the course of that interview, I met Bill Code, who was vice president of the company. And I don't know if any of you know who Bill Code was. He passed recently, but he was a very passionate person about the business we're in. And at one point, he wrote a paper called "Energy Conservation is an Ethic." And I have a Bill Code page on my website. Everything he ever wrote is there, including his book. You ought to read that paper if you're into this. He wrote the paper maybe 20 years later, but he basically gave me that talk in the course of the interview, and it inspired me. It like changed my life. It really did. And I walked out of that interview and decided, I'm going to give this building systems thing a try. And here I am, right? It worked out pretty good. Okay. So from 76 to 84, I sort of worked for McClure Engineering, and I started out as a field tech. The audience you're targeting. And in a way, part of the reason I'm doing this is I think you're trying to grow versions of me. I mean, that's what you're really trying to figure out. And so I was thinking, well, maybe if I told you how that happened, that would be handy. So that's why I'm doing this. If you're out in the field, all you folks that are in the field, if you're dealing with problems with systems, you're going to learn how to do controls, right? Because 80–90% of the stuff's going to come down to some control issue. And I got into that, and I really liked controls. And McClure did their own control system design. And so I started doing control design for some of their projects. And then that, you can't design controls without understanding the process, right? And so to design the controls, I had to learn HVAC, and that led me to being an HVAC designer and a project engineer. And through all of that, I was mentored wonderfully. I have had a blessed life in terms of mentors, and Phil Sutherland's one of them. That's it. When Kath and I got married, he actually showed up at the wedding. But that's really important. I'll talk about that a little bit more, actually. Well, somewhere in the middle of that, Siemens, MCC Powers at the time, was looking for a systems engineer, and I just loved controls. And I was like, oh, I'm torn. I love McClure, but man, maybe I'm supposed to be a control engineer. And kind of with their blessing, they literally said, well, maybe you should go try that. There's always be a desk for you here if you don't like it. And so I kind of went on a sabbatical and went to work for Siemens Powers at the time. And what was really good for me about that was it immersed me in a control system. And what I discovered subsequently is if you get immersed in a control system from one vendor, you probably can figure out the other ones pretty easy. And so that experience set me up to be able to, to do what I did later in my career, which was be involved with lots of different systems. Exposed me to process control. I crashed my first control system at Procter & Gamble plant there. I kicked the short version of the story. I changed the COV limit on some. Well, here, this will age me. I was excited because we had just kicked the baud rate on our trunk up from 1,200 to 2,400 baud. And it was like, holy crap, now look what I can do. And I changed the COV limit on something because I thought, oh, now I can see that problem that I think's there. Well, I missed a decimal place, and I crashed the system. I remember sitting there watching the screen, and then this DEC mainframe starts doing all these disk accesses, and then the printer starts spewing stuff out, and it's aborting processes. And it eventually aborted kernel in the operating system because I'd put so much traffic on the network because the point at the COV limit I put in was fluttering. It just flooded the network and crashed it. So that was the first time I crashed a control system. Learned something there, okay? It gets really quiet, okay? But I also discovered in doing that with Siemens, a lot of designers didn't understand control systems, which is a little scary. And it's kind of still true in a way, and that's a scary thing, I think. Having done that, I was actually wanting to go back to McClure because Siemens was kind of wanting somebody to put in what the sales guy sold, not necessarily what made sense. And that bugged me. I get it, I guess, but it bugged me. And I was about to go, I was actually having lunch with Jerry and Phil and working out the deal, and mechanical contractor I'd been working with, I did St. Louis Union Station. He said, well, wait, come be our field guy. And so I thought, well, I don't know. And Jerry and Phil and Bill were like, well, yeah, that'd be a really good experience for you. Go work for a mechanical contractor for a while. You might like it. Still be an office here if you want. So there's something right there, like encouraging somebody to go try something else, even though at some level, because I've had that happen now. I've encouraged people to go, you ought to try that, and then they leave. I thought, crap, Darren, I didn't know you were going to leave. But no, it's a good thing in the big picture, and they were encouraging me. And so I went to work for this mechanical contractor, and I blew up my first duct, the MCI building. That's where I blew up my first duct, and that's how I learned about lags, which I'll talk about later. And so part of this whole thing about being out in the field is it reinforces the theoretical lesson. And so I think the stuff that you want to do that gets the hands-on thing happening is really, really important. Because I wouldn't know what I know had I not been out in the field. I wouldn't know what I know if McClure hadn't been a hands-on company that after you designed it said, go start it up, make it work. So that's really, really important. And that's a thing that I think is lacking in the design community right now. A lot of designers don't get out in the field, and I think that's a problem. Like I try to take them out in the field with me if I can when I'm working jobs. So eventually I went back to McClure because I didn't like gambling. Basically contractors, you're kind of gambling, and I'm not a gambler. And I did a lot of healthcare work, and I also migrated their control specs from pneumatics to DDC. The industry isn't at that point where people were starting to do DDC on the central plant, and they had a really good pneumatic spec, but it wasn't working very well for DDC, so I ended up migrating their spec. And that was an interesting experience because all I ended up, when I wrote the spec and I developed a bunch of standard details and stuff like that, all I really did in the spec was, it was like two parts. One was a very, very specific, here's the pieces we will allow in our system. And you couldn't have built one of our control systems using any one vendor's materials. Like there is stuff from some of the vendors that was no good. And we don't want that switching really. We want a different one. And so I had that. And then the second part of the spec, sort of the installation part, which just sort of like, so I really messed this up once, so let's not do that again kind of stuff, right? And so I get all done right in this spec, and it's like 110 pages long. And so I go show, I remember going into Jerry's office and Phil standing, I said, well, I'm done, that's good news. Bad news, it's like 110 pages. And everybody was like, oh crap, we can't have a 110-page spec. Well, let's get everybody, we'll have a meeting, talk it through, see what we can eliminate. And we had the meeting, and it ended up being 125 pages because I'd forgotten some stuff. So anyway, and then getting that to happen, getting that, you had to enforce, it took about 3 years before people realized, oh my God, they're serious. But then after the fourth year, literally every one of the vendors basically, one way or the other, came into the office and said to one of us, "Thanks for giving us a spec that lets us do what we're capable of doing." In other words, if you go out to bid with a drawing that has a dotted line around the building and says the control contractor shall install controls, and oh, I'm going to buy the low bid, well, it's not going to work out so well. But if you define the details, it levels the playing field. And that's what we had done. And it just takes a while to get people to realize, oh, they're serious. You know, I'd got in the field doing site visits and like, see this detail in the drawing? You didn't do it like that. And they'd say, well, nobody does it that way. And I'm like, well, yeah, that's why I drew the detail on the drawing. And so anyway, I did that until '97. But I'd always wanted to live in Oregon, and I actually had a life event, sort of almost died kind of life event, where you kind of realize when that happens that, you know, maybe this is a finite process and I need to do some of the things that I really wanted to do. And so I sort of, I guess you could say, opened my heart to move into Oregon, and like in 4 months I had a job in Oregon, basically. And I ended up going to Komatsu Silicon America, and I was their system owner. Dennis called us system owners, not facilities engineers. And I basically, like when I got there, this part of our clean room was up and running and we were building this part. We basically grew wafers. We made wafers that, you know, like Intel grows their chips on, so we grew the crystals and sliced and diced them and stuff. And so I was there for that plant coming out of the ground and bringing it online and all that stuff. And I was basically HVAC system owner, process exhaust, you can see the list. I inadvertently became the fire protection system owner because in a meeting they were talking about sprinklers, and I said, oh, I think in something that they cover that. And everybody looks at me, and Fred says, you understand sprinklers? And I said, well, I did a little of that. And Fred looks at me and says, you're a fire protection engineer. Now, reason I bring that up, I really didn't know diddly squat about sprinklers compared to what the fire protection issues on a site like that, whole multiple orders of magnitude different than a commercial building. But guess what I learned about it, and guess what I understand now, and it made me a better engineer, a better person. So in some ways, taking on something you don't know anything about is a really good way to learn. So I encourage people to do that all the time. You may want to not do it in a meeting, though, because you may want to have a choice about it. Do I have to be the fire protection engineer? Well, semiconductor crashed. Like the whole economic premise for building that fab was a $200 wafer. And in, I think it was like late 98, Korea flooded the wafer market with wafers below $100. And we couldn't sell wafers. We were losing wafers on pennies a wafer, like 99.95. Oh, the guys down the street, Walker Siltec, they'll sell them for 99.94. We're going to them. It was really that close. And what was interesting about that was to see an economic cycle from the inside. Like we built that plant, $500 million plant, on time, on budget, and we never made anything. It idled, and it sat idle, and it became Solar World. They make solar collectors. Now our process was really good for like the PV that you'd make for solar collectors. So seeing that on the inside and seeing it go, like I'd see stuff like, hey man, this could save, if we did this at measure, we could save, I don't know, 5-10 cents a wafer and get blown off. Doesn't matter. To where that 5 or 10 cents a wafer could have been like, well, we could sell it cheaper than Walker Siltec when that economic downturn happens. So there's a lesson there, a broader lesson. Like there's cycles to everything in this business, okay? I left there and I went to PECI. At the time, PECI was this little group, that's PECI when I went there. They ended up being about 450 people, and then they got absorbed by a company called Clear Result. But at the time, they were a little not-for-profit.org trying to promote infrastructure for the commissioning industry and a bunch of engineers, and that's what we did. And in doing that, that's where I learned I could teach technically and teach hands-on stuff, but I had to do it my way. Like the first time I went to teach, Carl Stum took me with him to the Energy Center over in San Francisco, because he wanted me to do a thing on the field perspective on some of the stuff. And I had gotten a bunch of pictures together, and I was told, you can't use pictures, these have to be bullet points. And I'm like, oh my gosh. And I'd never seen PowerPoint before that, to be honest. So I had my little bullet points, and I'm sitting there waiting, and when Carl said, now David's gonna talk, I wasn't sure if I was gonna like barf or faint, you know, or both, possibly, because I was so freaking scared about getting up in front of people. And now I'm actually pretty calm about it. But I stood up and I started my PowerPoint, and somebody asked a question, and I said, oh, I got a picture of that. Can I show a picture? And Carl said, sure. So I showed a picture, and all of a sudden I was just fine. So what I learned from that is you have to do things sort of in a way that makes sense to you. But we also discovered that that's where I started to realize people are really thirsty in this industry for that kind of information. They don't want me to just talk about a chiller. They want to see what a chiller looks like. So putting up a picture of a chiller and saying that's a chiller and let's talk about that is way more effective, at least in the classes we're doing, than having a slide that says chillers make water cold and they have hot water coming out and they use electricity or steam or whatever they're using. So in my experience, graphics as a teaching mechanism are really powerful, a much more powerful way to communicate stuff. And so I do a lot of graphic stuff, Let's see here. Oops, wrong direction. Okay. So did that for a while. When PCA got really big, they became more programmatic, and I'm not a programmatic kind of person. I'm sort of an engineer. And I'd met Jay Santos, and I realized at one point he's so subtle about this stuff. I realized like 4 weeks after I'd been sitting around having a glass of wine with him that he'd basically offered me a job whenever I wanted it. And it's like, oh, maybe I should do that. And so I went to work for Jay. And so I do a lot of existing building commissioning. I do a little bit of new construction, but not so much. And I do a lot of hands-on training. I do third-party control design, but like right now, like the past 4 years, 50–60% of my time is either doing training classes or getting ready to do the training classes. Because the hands-on classes, like for instance, the classes I do with Marriott, we pick a Marriott that's not in very good shape. Everybody shows up there, and then we use the building as a living lab, and they, retro-commission the building. So to do that, I got to get in there ahead of time and figure out, well, here's where we're going to focus and get data. So at this point, I'm probably spending 50–60% of my time doing that kind of stuff, and I like it. And Jay thinks I have a knack for it, and he encourages me to do it. Even though like I'm sort of the leadership role in the not-for-profit division, basically, we joke about that. There are more profitable things you can do than train. But I think that's interesting in a way. Like, everybody wants training. But it's sort of like when you say, well, here's what it costs to do that. Well, I'm not sure I want to spend that. I think somehow we need to change that. I don't know how, that's a question, not an answer. I mean, I don't know, but I think it's an observation that merits consideration. So anyway, go back to the airplane mechanic thing, because I actually, like I said, I taught flight line labs. And so I got new jeans. You probably see much newer jeans. But I was teaching flight line labs, and like the first week, like a month ago, I'd been the person taking the flight line lab, and now I'm the lab instructor supporting the flight line lab. And I realized a couple things that I think are really important. One is it's one thing to understand something, and it's a totally different thing to be able to explain it to somebody. That takes a deeper, more profound level of understanding. And to me, that's part of what's exciting about doing the teaching thing, because I'm always learning. Like, the field classes are a little crazy, because I'm trying to stay a couple hours ahead of what some of these students are doing, and they've gotten all passionate about it, so they're like excited. And so you learn a lot. You also learn to say, I don't know, but I'll figure that out and we'll get back to you, okay? But that's a really important thing I learned. Another important thing is, and this goes to the hands-on thing, applying the knowledge in a practical way, doing something with it after you heard it, is basically going to enhance your confidence in the theory, okay? It's one thing for somebody to say, yeah, if you write this control logic, the fan will start. But it's another thing to plug the control logic into the controller, hit run, and see the fan start, or not, whatever happens, and then figure that out, right? And so applying it is really, really important. You guys probably know there's metrics out there. Amy Smith told me this. She's an educator of educators. She's Michael Ivanovich's bride. Like, if I sit here and yammer at you like I am now, you're going to remember maybe 30–40% of it. If I could get you to write something down, you might remember 50–60% of it. If I can get you to do something with it, you'll remember 80% of it. And so that's sort of the goal with these hands-on exercises, to try to get people to do it and try to figure out ways to do it, like I can't take 80 people in a mechanical room, but the models let me do that. So try to figure out how ways to do that. So that's part of what we're working on. You'll discover that you'll misapply the theory. And that's okay. It's one thing to misapply the theory in a learning environment. It's another thing to misapply the theory in the real world when everybody's counting on you haven't done it right. So applying your knowledge in a learning environment, hands-on, yeah, crap, that wasn't right. It didn't work the way I thought it would. Well, next time it will, okay? And then, like if you're in commissioning, every one of us has been that guy right there. Like you're sitting there before this test and you're thinking, something doesn't seem right. And about 30 seconds later, oh, now I know. and so you learn from that. And so when I teach functional testing, I actually there's a Mercury Redstone 1, I don't know if you ever saw that there. It's a boilerplate mercury capsule, and they hit the launch button, the rocket lifts off 4 inches, settles on the pad, and the whole escape mechanism deploys. And there's like this embarrassing failure for NASA, but like in a way, if that wouldn't have happened, Alan Shepard or Gus Grissom or John Glenn could have been sitting on that thing when it happened, and then they would have ended up in a space capsule on a time bomb with no way out. And so because of this test that failed, the launch team, the designers, NASA, learned, oh, we need to fix a few things before we shoot this thing off with somebody in it, and they did, and it made it safer. So a failure, the silver lining on a failure is there's a lesson you can learn that'll help you make something better. So, a lot of guys I work with, we figure if you aren't breaking something every once in a while, you probably aren't pushing it hard enough. I mean, we're test engineers are trying to push the envelope, basically, right? So something's going to break, okay? Another thing I learned, things that are obvious to you are not necessarily obvious to other people. First, one of these signs, I just started rolling on the floor laughing at it. But I worked with Merrick, I said, there's a need for that sign, right? And I can see Kathy, my bride, she's a girly girl, right? And you ever see the little brass sidewall ones, right? I can just see Kathy, oh, isn't that nice? I can hang my dress up and let the wrinkles hang. I can just see her doing that, because she doesn't know. It's obvious to me, not obvious to her. So that's an important thing, because if you're trying to teach, you have to remember, I think, that just because this is making sense to me may not mean it made sense to all these people I'm talking to. And so one of the challenges there, I think, in the current learning environment is trying to do web trainings. It's really much harder for me doing a web training when I can't see what people's expressions are. Are they asleep? Is it quiet because the audio's off? Do they all look it really is different. Like some of you seem to be nodding your head. Some of you, I think it's maybe after lunch, and I get that. But it's really valuable, important feedback. And Ryan and I are about to experiment with putting a camera in the classroom so that when I do a web thing, not only can they see me, I can see them. And that was the result of I was doing some web stuff for Jay and Brian for the Presidio thing. And I just, on a lark, I discovered this Camtasia software would record my video camera in addition to my screen, so I did it. And so in the video, when I'm just talking about, here's what we're going to do in the model, I just have me zoomed in. But then when I started working the model, instead of making me go away, I made it go down in the corner just as an experiment. And the next day, Jay emailed me and said, hey, that was really good. I really liked that I could see you down there in the corner. Somehow it makes a connection. I think that's an important thing. The people thing's probably just as important as the technical thing. So just another lesson, I guess. So all that was, observations even back then led me to wonder, well, how do we communicate this stuff to somebody coming in the industry? Like at this point, I started in '76, now it's 2017, 2018, so I've been doing this for a while. And there's a need to slow down a little bit. I don't plan to slow down a lot, but I just can't go the way I used to go. And how do we transfer that information, which I think is a fundamental question that you guys are basically trying to ask yourself, right? And so one of the things that I think is hugely important is mentoring. This is a picture, this is my first technical mentoring experience. I was in 8th grade and I built an electric motor. And I did a blog post about it, so I won't tell you the long story. You can go look at that if you want. But the key point is, I was doing really great until I got to making the commutator. I was using these instructions, and it said you needed a round piece of wood. And I didn't have a way to make a round piece of wood. And I went and visited Ted Malik, who was this applied physics guy, worked for Westinghouse. I grew up in central Pennsylvania, in Pittsburgh, western Pennsylvania. And Ted was just passionate about physics and like, he's a theoretical physicist, right? And he was talking to me and, no, I don't have anything to make a round piece of wood, but why does it have to be round? He asked me that. And it's like, oh, it doesn't have to be round, does it? And so I made it, the motor worked. And so there's a couple really good mentoring lessons there. Like Ted hinted, but he didn't tell me the answer. He asked a question versus saying, it doesn't, make it square, it doesn't matter. He said, why does it have to be round? He showed up at my house later that evening to see how it worked. So they showed, ongoing engagement and stuff. So those are all good mentoring characteristics, I think. So I've had really good mentors all the way through my career. That's John Moyne. He and Bill Toomey mentored me as an airplane mechanic. And I, to this day, still say stuff to students that John said to me. Like the most poignant memory I have is I used to, like an airplane, so think about this as a side note. So 2-year program, right? I am now a licensed airplane and power plant mechanic. I can sign a logbook that this plane is safe to fly in. Now, I think if the aviation industry can do that, there's probably a way to do it for what we're talking about, right? And part of me thinks maybe we need to make it, like I didn't have an engineering degree, I didn't have a PE, but I had an aircraft mechanics license, and that was a professional thing. That was like, I'm gonna sign a logbook someday. And so I'm working on this plane, and I would wake up in the middle of the night on flight line lab days or after, and I couldn't remember a step. And what had happened, I realized, was I'd be talking to students while I was safety wiring something and explaining it. And so my mind was engaged with the student, not with twisting the safety wire. And that all played out in my head at night, and I couldn't remember. I actually went to the hangar at 2 in the morning once, popped a cowl to make sure I hadn't forgot the safety wire. So the process I went through ingrained a sense of like personal ownership and responsibility that made me want to do it right and made me feel like, hey, this is important. Somebody's going to go in this plane and like learn instrument flying tomorrow in real instrument conditions. I can't mess this up. So, it made you feel good. So anyway, I was doing that and I was triple checking myself, and John came out and he said, David, he said, you're my lab assistant, you're running 100-hour inspections, that's the same as an annual, I'm signing them off. Why are you so worried? I trust your work. You should trust your work. And I've said that to students who, they're experienced, but they're having a hard time letting go. I went in with the inspection sheet there. I can still see the scene. Bill Toomey's sitting there with a cup of coffee, his feet up on the desk. John's sitting there. They're talking. I say, yep, you can sign it off, John. And John takes the logbook, turns it to me and said, no, that was 100-hour. You can sign it off. That's a whole different level of engagement. Like you're picking up the pen and I'm going to write, I, David A. Sellers, blah, 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 AP 16946. That's really profound. Like when I see a drawing, I have that same sense of profoundness. So part of the reason I'm telling that story and bringing it up, like you've been talking a little bit about like how to elevate this, how to make this significant. Maybe there's some angle to that. Like I realize this isn't going to be a regulated thing like the airlines, but maybe internally there's some way that you could, build something into the program that says, hey, this is the thing of value. We respect this. Your signature is going to go on it somehow. I don't know. So anyway, just a thought. Bill Code, tremendous mentor. Phil Southern, I mentioned him. Phil's 82, and he's still taking young engineers from McClure out in the field and saying, this is a ball valve. Let's make a system diagram. Yeah, I know you don't have time to run a load by tomorrow, but we can estimate the load. It won't be exactly right, but it'll be good enough. Stay calm. He's still doing that when he's not playing golf, okay? I want to be like that when I grow up, right? Jay and Ryan, Jay creates this place where I can do what I do. Like I said, it's not the most profitable part of our business, but we think it's an important part of what we do. Ryan pretty much lets me do what I think I need to do at the Energy Center, which probably gets him some crap sometimes, but none of this would happen without that. And then Kathy, my bride, there's the other side of this. I think that's important. Like we get all focused on technical stuff. I think it merits bringing the personal side in. People are looking up to us at some point, And I think it's important for them to see there's more to us, there's more to life than the technical thing. Like I've had students tell me your class changed my life. That's very moving. It's also, two of the other moving comments, one person said, I really learned a lot, and I liked it when you talked about Kathy, you called her your bride. They remembered that. And another person said, the slides were great, but so is your screensaver. Like I used to have family pictures running the screen. So I think that's making a connection, and I think that's an important connection to make. So that's touchy-feely, I'll get off that now, but just thought I should make that point because I think it's important. Aviation's got a really long, mentoring's how they do it. Like they don't stick a first officer in a 737 and say, go fly it. They stick the first officer in a 737 with a captain in the left seat so the first officer can ask pertinent questions like, why is there a cloud? Or why is there a mountain goat in the cloud, right? And learn from that experience, right? And when you're learning to fly, which is basically a self-taught thing, there's still a flight instructor there to take over if you do something really, really stupid. So part of, I think, what we have to ask ourselves when we're talking about this is, how do we communicate what we're doing without breaking something, okay? Because you are set up to break things. And that's kind of one of the nice things about the models. You aren't going to break the model. Or if you do, you just say Control-Alt-Delete and start it up again, okay? Now, one way to keep people, comfortable, help them from breaking stuff is to foster familiarity with the fundamentals. So there's steady flow energy equation, right? So you can run them through that for conservation of mass and energy in a mixed air plenum and show them how all that works out. And there's all these really cool things, and you do all the math and do all the algebra, and basically you get to the bottom line. There's these other graphs you get to use, and ta-da, there's the relationship you want. You could do it that way. That's actually slides from a slide deck if somebody really wants to know. But what they really want to know is that, okay? And truth is, what I really want them to know is that equation right there. And then there's 4 others that fall out of that. That's what matters. And what I've discovered is, if I don't worry so much about the derivation and say, here's some bottom lines that came out of that hairy equation, somebody's going to get really inspired, and they're going to do the derivation anyway and learn it. And that's the person that's going to make the best use of that. So by giving them the bottom line, showing them where it came from, you didn't scare them. I'm math phobic, and so derivations like that used to make me shudder. And so what I did is I took all the math I could in college, even though I didn't need it. I had a mentor that said, yeah, take math. You don't need it, but take it. And that helped. I learned Calc 3 or Calc 1, taking Calc 3 basically. So I think by all these fundamental things, we have to foster a knowledge of that. I think we don't necessarily have to foster the derivations. The people that really need to understand that, they'll be inspired and learn it on their own. That's why I did it, right? And if we can get to these bottom lines, basically you can do some really useful things. Like those equations, if you plot temperature versus outdoor air temperature and ask yourself, if I had a perfect economizer, what would those lines look like? And you set up some ground rules. There's my mixed air temperature set points and stuff like that. And you basically ask your question. And I actually do this interactively. So this is a way that I teach economizers. Like, what's the outdoor air temperature position when the outdoor air temperature is exactly equal to the set point? And that's a pretty easy question, right? You almost want to overthink it. It should be the same, right? So that dot right there gets defined by answering that question. And then you just keep asking a series of questions. And what you discover is you can use those equations to plot some other points on this chart. And you can paint a picture of how a perfect economizer should work. This is running slow right now. So let me get to the bottom line. So you can paint a picture of how that perfect economizer should work. And you can add some other stuff to help you do diagnostics. But what that line means is, if I had a perfect economizer and I plotted outdoor air temperature versus mixed air or return air, depending on which you're looking at, I would have all the data points would be right on that line. Therefore, if I take that line and plot the real data on top of it and I get these clouds, that cloud's telling me about the dysfunction in the economizer, right? Does anybody know what that's telling us right there? This is when you're economizing, this is when you're on the integrated economizer. So you're 100% outdoor air, but you haven't gone to minimum again because it's not hot enough outside yet. And then you're back on minimum here. So what's this cloud? What do you think, hypothetically, what do you think that would be telling you? Any ideas?
You're going back to your minimum too soon.
Yeah, you're staying on minimum or you aren't coming off minimum. And then some of the time, this economizer is making air way colder than the design. And then if you, I took that slide out, but if you add the cooling coil on this unit, what you discover is there's preheat activity and chilled water activity right in there. Should that be true? No. And so the graphical presentation of the data makes it jump out. And so you can build relatively simple tools like this in Excel and use them with your students to facilitate their understanding of how a process works. You can start out by saying, let's draw the lines ourselves and think through the process, and then here's some data. Tell me what you think these economizers are doing. So we do that. There's also a tool called the Universal Translator. Anybody heard of the Universal Translator? It's not a Star Trek thing. If you have to remember, type ut.org if you want to find it, because if you type Universal Translator, you actually find all the Star Trek stuff. But it's a tool that has a lot of algorithms like this built into it. So the plus is all of these visual representations of data are built into it. The downside is there's a bit of a learning curve. It's a database, okay? And the big reason I don't use it is I already had the spreadsheets, and it's faster for me just to use my spreadsheets. But for somebody new, like your students, might be the perfect thing to hook them up with to help them understand how to use and analyze data. So, okay. So a lot of useful relationships fall out of these fundamental principles. Like the steady flow energy equation, at some point, if you mess with it, becomes that equation for pump power. And that equation is basically saying the pump energy is a function of the flow in the head. So everybody get that? So if I reduce the head, or if I reduce the flow, or if I reduce both of them, I'm going to save energy, right? So if you can get people to see that, and then they walk by a pump, that's a valve on the discharge of the pump. So what's that valve doing? Yeah, it's a pressure drop, right? So they see that, you've given them this, they can say, well, wait, the name, I bet they balanced it to the design flow rate. Right there, they can do a little bit of math and say, wow, here's about how much energy we might be wasting, okay? Just because you gave them, like, you didn't give them this, you gave them that, right? And a little insight. Another example, 1.0 HCFM delta T. In 30 minutes with that equation, and then another 3 or 4 hours with a spreadsheet, I was able to figure out that this unit at Komatsu was wasting $7,000 or $8,000 a year in energy. It's doing really stupid stuff. And I don't have time to tell that story. If you want that story, I actually wrote a paper about it. It's on my website. It's called basically commissioning for, it was up for the longest paper name in the world. But it was something about commissioning for clean room qualification criteria instead of energy efficiency, because the clean room was dead on. But man, the enthalpy of the universe was going up way faster than you need. I was like standing in a puddle of water coming off the cooling coil drain pan, watching steam get injected into the airstream. It makes no sense. No sense, okay? And I guess maybe something to mention there that might be useful here. That was the first, when I walked on site, excuse me. When I walked on site, that was the first unit I saw after I'd been through the hazmat training, and I'm finally out seeing my systems. And like I said, in 30 minutes, I had identified all those numbers. The operators were with me. They were kind of like devastated. They're like, well, how'd you do that? We go by this thing on rounds every day and log all that stuff. But how'd you figure that out? And I asked a question. I said, well, has anybody ever explained how a clean room works to you? Or psychrometrics? And they said no. And these were like experienced, really solid. They were from like subs, nukes, wastewater plants, process. They were around machinery. They understood machinery. They understood, like, I used to joke, like, if I couldn't get stranded on a desert island with Kath, I'd want one of them because they could build me anything I wanted out of like sand and bamboo, probably. You just had to define what it had to do, and these guys would build it. And so I decided, well, tell you what, why don't you guys on day shift every other Tuesday stay an hour late, and you guys on evening shift every other Tuesday come in an hour early, and midnight shift will pay you to come in for a couple hours. And we'll take turns, so we leave the control room covered, and we'll go find ourselves a classroom, and you can explain this plant to me and how it got built, and I'll try to explain psychrometrics and clean rooms to you. And we started doing that. And it totally changed things. Like, I used to get my pager go off at like 2 in the morning, and it'd be like, Wally, like, Dave, you got to get in here. The clean room particle counts are up. You know, you got to get in here. And so 2 in the morning, I have to go trudging into the plant, right? After I started doing this, and I was learning from them too. After I started doing this, I remember one night I got the 2 o'clock page, and I pick it up and goes, hey, Dave, this is Red. Hey, listen, I just walked by the PW makeup air system, and the coil is condensing, and when I looked at the outdoor air temperature and humidity, I don't think the dew point's right. I think we're running the chilled water too cold, don't you? And I'm like, Red, not a morning person, no coffee. Oh, crap, yeah, it's middle of the night. Never mind, I'll see you tomorrow, bye, click. So that was a really important thing right there, because now Red was empowered, and he was doing that, and I could go do other stuff. Plus, I didn't have to go into the plant at 2 in the morning. So, you know, telling people how things that work, the people that are charged with operating them, has a really, really powerful benefit. And so I think that's a really important thing for us to do. Okay. Oops, I hit the wrong button. There we go. And, you know, those relationships, along with like what Bill taught me, the desire to save energy and the need to save energy, can inspire you. Because what happens, like, if in that air handler I save a little bit of energy here, like say I reduce the static pressure a little bit. So that, remember that equation, if I reduce the static pressure, if I optimize that, then the fan doesn't have to work as hard, right? And so what happens when you take a bicycle pump and pump up a bicycle tire? What happens to the pump? It's hot. Same thing happens on a fan. You can measure the temperature rise across the fan. A lot of you probably have done that. That's called fan heat. So if I reduce the static pressure and I do reduce the amount of work the fan has to do, there's actually a little less load on the cooling coil, which means there's a little less chilled water flow required, and there's pump heat. It shows up a little differently, but there's pump heat. So there's a little less cooling that's required in the chilled water system, which means the compressor on the refrigeration cycle doesn't have to work as hard, which means the condenser pump may not have to work as hard, which means the cooling tower fan doesn't have to work as hard, and you don't use as much water. So there's all these ripple effects to making a little change there, all the way back through the central plant. And we don't usually talk about them. They're kind of like icing on our cake. Okay? And the same thing's true on the power side. You know, if I do something to reduce the flow rate of that pump, you know, there's losses in the pump. It's not perfect. The motor isn't perfect. The drive isn't perfect. We stop talking about it at the drive, but there's actually losses in the distribution system. That's why transformer rooms are hot, right? There's 2-3% loss between the meter and the load. And it's worse. Oops, wrong way. See those? Showing up, okay. There's 6-8% loss in the United States right now between those high voltage lines leaving this plant and the high voltage lines getting to the substation in your meter, okay? So we save a little bit of energy in terms of water at a flow rate. It ripples all the way back through that. And then I just like visuals like this. That pile of coal, all of that mass except for the fly ash ends up in the atmosphere, okay? And the current heat rate right now is like 10,000 BTUs in for 3,400 some BTUs out. So think about what that means. I save a little energy out at the end of the system and how that ripples back and not only affects my bill, it affects us societally, right? And so I think coming up with ways to explain that to people sometimes helps, because now it's like what they're doing is part of a bigger thing. It's part of a better good, a greater good, right? And so these are just where those metrics came from. It's from a thing called eGrid. Barry Estes, one of the guys I work with at Marriott, he wanted me to make that a little more personal. He liked it, but they wanted to explain to their GMs and their desk managers what all this stuff meant. And so I decided I'd figure out what it looked like for an iPhone. And so I basically did all the math. And what I discovered was, probably spend 20, 30 cents a year keeping your iPhone charged. But something like 71% of the energy is lost that left the power plant to charge your iPhone, okay? And it puts a little carbon dioxide and sulfur and NOx in the air, okay? And you can look at that for a coal-fired plant, and the numbers, the emissions go up. The costs don't change that much, but the emissions go up. But 20, 30 cents a year, it's like, maybe I don't even need to unplug my charger when my phone isn't, because you're wasting the energy and the charger losses. But so then I said, well, what's that look like? This is one of the air handlers that we have a model of that we'll look at. I said, that's a 20,000 CFM air handler. So I said, what if we got a better schedule on that thing and saved an hour? What would that be worth? Basically, for a typical day, that unit's using in the range of $120 to $140 worth of energy and putting that many pounds of carbon in the air, okay? That's what it takes to cool the ballroom. I guess, I did for a day. So now, to put that on human terms, I said, well, what if I had some magic device that I could put in my tennis shoes? So when Kathy and I go for our walk, it would charge my iPhone. There's actually people working on that. I assumed an iPhone charger efficiency, the efficiencies they have aren't anywhere near that good. But if they achieved the iPhone's charger efficiency, Kathy and I could legitimately probably charge our iPhone on our walk every day. We'd walk slower. If we kept the same metabolic rate, we'd walk slower because some of that energy would be going into the iPhone, basically. But we could charge the iPhone. If I said, well, what it would take to run that air handler for an hour, it would take 13,000 people walking with a little device. And all our cords would get tangled up, right? So that is a staggering thing to me. Like, you think about that, how casual we are about this energy that we spend. On a human scale, if we had to recreate that, man, forget it. It's not going to happen, right? And so I think trying to get people to understand that, including our students, to realize, like, wow, if I can learn how to do this, if I can make a little change out at the end of the system, it ripples all the way back and it addresses this problem, That's important, I think. So, the whole climate thing, that's like a rife with controversy thing, right? But if you're just logical about it, and you look at the Earth at night, and you see all those lights, and you think about the emissions, it's like we have to be having some kind of impact. We just have to. Granted, there's always been CO2 cycles, but look at the one that we're in now, right? And we have to be having an impact. And like, the cautious engineer side of me is like, do we totally understand the atmosphere? Do we understand how the atmosphere works? No. If we understood how the atmosphere works, the weather forecast would be right every day. It would. Okay? It's just a bunch of forecast models. So we're doing big stuff to something we don't understand. It might be good to be cautious about it. That's sort of what I think. Politics and all that stuff aside. And then this is one of my favorite quotes. We don't inherit the world from our ancestors. We borrow it from our children. I used to, like in the 70s and 60s, I thought I was saving the planet. I don't have to save the planet. The planet will save itself. If we don't get smarter, the planet will make us extinct and say, I'm going to wait for somebody more intelligent to come along and see how it works next time. I'm worried about what's going to happen to our kids and our grandkids. And that's the generation we're, in a way, trying to reach out and touch and engage in this. So how do we do that? How do we get the younger generation engaged? One way to do it, like this worked for me. I was like totally fascinated by the space program and aviation. Like, until I took the job at McClure, all I ever thought about were planes, rockets, and the occasional pretty girl. That was it. That's all I wanted to do, all I wanted to think about. So you can engage young people with technology. In fact, Kathy had an example like yesterday. Kath and I are trying to plan this trip with Chris, one of our sons, and Jake, his son. They live in Edmonton. And so we said, well, what if we flew to Edmonton, took the train across the Rockies, and ended up in Vancouver, British Columbia, and you could see the Rockies, and it'd be a really cool trip, and do it for spring break. And Chris liked the idea. He said, let me talk to Jake about it. And so I guess Kath said she was talking to Chris yesterday, and he had talked to Jake about it. And Chris said initially, Jake was like, And then Chris goes, well, there is Wi-Fi, and you could send pictures to your friends and stuff. And Jake's like, there's Wi-Fi? I could send pictures, I could text. And so like, now we're engaged, And so, leverage the technology and like stuff that you guys are talking about. You sit in front of the graphics, you can teach people to do that, they engage. And the technology is fascinating. There's the shuttle's main engine, and look at the statistics on that and the control drive. Our systems are equally fascinating. They're just as complex, they've just as many moving parts. The nice thing as a mechanic that I always appreciated was, I'm not going to sign a logbook on a building that's going to fall out of the sky. It's just a little less stress, right? And so the fascination's there. People don't realize how technically complex and interactive buildings are. And I think that's part of what we have to do if we want people to engage. It isn't about, sweeping the floors and cleaning the toilets. It's about keeping this big central plant running, optimizing it, adapting it to all the changes that happen. A friend of mine, he's a facilities engineer for a hospital, and he realized his little girl didn't want him to come on Parents' Day to say he was a facilities engineer because she thought facilities meant, I need to use the facilities like a restroom. And she was, so maybe we need to call it something different. I don't know. Just saying. Now, the one thing we don't have going for us right now is multiple years of operation without failures. Our systems are rife with failures, and they're insidious, like that clean room. Guys in the clean room loved it. Perfect product, perfect specs. It was a disaster from an energy and a sustainability standpoint. And so that's what we need to work on, and that's what we need to, train the kids to do. And there aren't a lot of space shuttles, but there are a hell of a lot of buildings. Like one of the visuals I got walking out of McClure's office that day was, their office was North St. Louis, and Lambert's up there. And like the standard arrival route back then, the planes would fly in over St. Louis and deploy into a stabilized approach coming into Lambert. And there's a 737 coming down final. And I love that plane because I don't know if you ever looked at a 737's wing, but it's like a technical masterpiece. It's just an amazing wing.